Okay, guys, quiz should have pretty much timed out by now. So we want to go ahead and pick up where we left off last time. There was one question back in Chem 101 and about the quiz. And I think that was the one regarding the isotope and how do you get an average mass for a specific element based on two known isotopes. So you actually have their mass numbers there. And you've also got their percent abundances there. So remember, there is an equation for that we talked about back on Friday. And basically, if you want to get the average mass, remember that it's a weighted average of the various isotopes. So what you have to do is sum together the percent abundance, but remember, you use it as a fraction. So if it's 11%, you don't put 11% in there, you put 0.11 in there, right? So you undo the percent. And then you multiply that by the actual mass of the isotope, which was given in the mass number there above the symbol. So you do that for both of them, and then add those two results together, and that'll give you the weighted average for the isotope, okay, or rather for that specific element, accounting for the relative abundances of all the isotopes. So if you're not sure on that one, go back to Friday's notes and find that equation and make sure it makes sense. All right, so let's go ahead and pick up where we need to now. And what we're going to really focus on today is actually nomenclature or naming of ionic compounds, okay? So first of all, just a real quick review of what's a compound. And the video kind of went into this, and I think you guys pretty much know already. But if I have something like CH4, okay, that's an example of a compound. Now what that's telling me is that I've got a unit, a molecule, if you will, okay, that actually comprises of a carbon atom and 4 hydrogen atoms all bonded together, either ionically or covalently. The same could be said for H2O, which is water, right? That's a molecule, a unit, right? And it's an oxygen atom bonded to a hydrogen and a hydrogen, okay? Now, those are both nonmetals combined with other nonmetals. So that tells us that those are covalent compounds where the bond is actually formed by sharing electrons. Then the last one, the NaCl, which is kind of where we're going to start this thing. That's an example of an ionic compound. And that's one where we actually have electrostatics holding these things together. In other words, differences of charge. So we know that, and this came from the video, I can have sodium 1+, because sodium has a tendency to lose an electron to look like a noble gas. And I can have the chloride ion. Chlorine has a tendency to gain an electron to look like a noble gas. And notice that you have a 1+ charge on one ion, you got a 1- charge on the other. And it's that difference in charge where one's being a positive charge and one's being a negative charge that are holding those two particles together, right? Because we know that opposite charges attract. All right, so I want to focus first on these ionic compounds. And again, how do I know whether I've got an ionic compound? Well, an ionic compound is always going to be a metal ion combined with a non-metal ion. So in other words, we're looking for something over on the left-hand side of the periodic table, combining with something on the right-hand side of the periodic table. Metals tend to be over on the left, the non-metals tend to be over on the right. Okay, and we sort of showed this down here where I have metal ions having a tendency to lose electrons, non-metal ions having a tendency to gain electrons. Metals like to carry a positive charge, non-metals like to carry a negative charge. Those two charges come together as opposing charges to hold these two particles together, okay, hence the sodium chloride. The other thing also to show here is that when I come up with the formula of sodium chloride, and we'll practice this a lot more as we go through today's discussion, notice that when we come up with a formula unit, which is what we call this, the charges on the individual ions have to cancel each other. I can't have a net charge on a molecule or a compound. Okay, otherwise it would be an ion in and of itself. So the 1+ and the 1- have to cancel each other to give me a neutral overall compound. Okay, so again, we're going to practice that more as we go. So there are various types of ionic compounds, and each one kind of has its own naming scheme. Now, the naming schemes are very well related, so once we get one down, it's kind of easy to get the others. Now, the type 1s deal with what we call main group metal ions. Now, what this means is that the ions over, or rather the metals on the far left of the periodic table over in group 1A and group 1B, those tend to be our main group we go over across to 3, and I can show you this on a periodic table. This is where it's nice to have one hanging in the classroom, but we don't. Well, let me go over and show you this in the periodic table real quick. I'm going to leave this momentarily and go to my files, which I have to find. There they are. And I believe over here somewhere I've got, here's a nice color-coded periodic table. Let's look at. Okay. So notice the blue elements over on the far left. Those are main group metals. Now notice sort of the dark pink ones in the middle. Okay. Those are the transition metals. And then we go across to the greens over there. And if you look across, the first column of green, starting with boron, carbon, nitrogen, if you move down, there are actually some metals down toward the bottom in there as well. Okay. But usually when we think of your main group metals, we think of things like sodium, magnesium, calcium. And if we move across to the greens, you could have aluminum, you could have indium, tin, lead is over there, for example. Okay. So there's kind of a delineation in that green region between the metals and the non-metals. And if you go very far to the right of the greens, that's where your non-metals are. Things like nitrogen, oxygen, fluorine, chlorine, bromine. Okay. But keep in mind, metal-wise, we're not talking about any of the pink guys. The pink guys we're going to come back to. But kind of keep in mind of where you are in the periodic table here. So we can always pop back to that as we need to. So let's go back to the notes here. All right. So we're talking about these main group metal ions here. So none of the pinks. All right. So that being said, let's think about how we name these. So let's start with the one we know. We know NaCl. That's the one we just wrote up. Sodium carries a 1+, chloride carries a 1-. I think everybody knows how to name this, right? Anybody who just want to tell me what the name of the formula unit for this compound is? I think you guys all know it. What's the name of it? Somebody want to just chime in?
Salt.
That's what we call salt, but what's the fancy name for it? Yeah, you're right. That's table salt.
Is it sodium chloride?
Sodium chloride. You got it. We'll write it down here. Very good. Yeah, if whoever said salt, you're absolutely right. That's also just regular table salt. All right, so how did we name this thing? Well, what we did, if you kind of take this back to just sort of a simple set of rules we could follow, is we took the metal element or ion name. That's where the sodium comes from. I'm just going to put ion in here because the metal ion name is the same as the element name. And then what we added to it is not chlorine. We don't call this sodium chlorine. So we're not just kind of sticking the two element names together. What we're doing is we're taking the non-metal element root, which is the chlor part. You drop the INE and you replace it with an IDE. Okay, so it's the non-metal root. Plus the suffix IDE. Okay. So that's where sodium chloride comes from. All right. So now if we do a couple more of these, another simple one you could do would be this. Let's just write down the formula here. KBr. One thing I like to do just as I go through these is I like to just verify that I got the right formulas. So if you have your periodic table handy, you'll find potassium there. You'll notice that it's a group 1A. So it's over on the far left part of the periodic table. Okay, things like that, like sodium and potassium, have to lose an electron to look like the previous noble gas. And then the bromide is a halogen. It's way over there in group 7A. So it's going to want to grab an electron to look like its next nearest noble gas. In this case, it looks like it's going to be krypton. So it's going to carry a 1- charge. So again, notice the charges are going to cancel each other. Now, if I want to name this according to the scheme, what are we going to have? Well, we use the metal ion name, which is just potassium. And I think the periodic table I gave you guys has the element names in it, so you don't have to memorize those. And then what do we turn bromine into? It becomes what?
Bromide.
Bromide, good. So see how we did the very same thing here that we did in the case of the sodium chloride. We drop the INE ending and we replace it with the IDE suffix. All right, let's do one that's a little trickier here. If I wanted to form, let's say, a compound between calcium and phosphorus, okay, let's do that. So calcium is here, phosphorus is here, all right? But this one's a little bit trickier because now if I want to get the right formula for this thing, and let's try to get the right formula before we name it, I have to figure out what the charge on the calcium ion is, right? So if I go back and take a look at the charge on the calcium ion, it's over in group 2A. So that means it needs to lose what? 2 electrons to look like argon, right? So in this case, I'm going to carry a 2+ on the calcium. Everybody see how I got that? Okay, it's over in the column next to sodium and potassium and those guys. So it has to lose an extra electron to look like its previous noble gas. And then this one's kind of like the quiz, right? I think, matter of fact, it might have been the answer to the quiz. So if you got something like phosphorus, it's over on the right-hand side of the table. So it's going to have to gain electrons. How many does it have to gain to look like its next noble gas, which looks like argon? How many electrons would it have to grab to look like argon?
3.
3. Yeah, you guys are good. Very good. So that's going to carry a 3-. Now, what do you notice about those two charges? Are they going to cancel each other out?
No.
No, not really. They're not equal, right? So notice that if I cancel, the 2+ will go away, but I'll be left with a net 1-. So what I have to do now is I have to now monkey around with the relative numbers of calcium ions and phosphide ions that I've got to make this thing work out so the charges will cancel, okay? So one way I could do that is I could say, all right, if I've got 3 calciums, I'm going to put 3 downstairs here to specify that. Notice that the 2+ times the 3 gives me a total of 6+. Now, how many of the phosphide ions do I need to get the 3- to a 6-? So I need an overall
2.
6-. Yeah, so 2 times 3 is 6. So I'm going to drop that 2 down here. Okay, so notice how I had to actually adjust those subscripts, and I actually represent these as subscripts to tell me the relative number of each ion I need to make the charges balance out. This is the best way I can do it. The only way I can do it with whole numbers. Okay, so, or I should say the simplest way I can do it with whole numbers and keep those 3 and 2 as small as possible. So that's how I come up with the formula for that. Now, using our naming scheme, what would we call this compound? So what's the first part? What would we call the first part of it? We'll just write it as we go.
Calcium.
Calcium, good. It's the element name. Now the harder part, which still isn't terribly hard. What do I call the second part? Remember, the element is phosphorus. So what do you think I would call that?
Phosphide or
Phosphide,
diphosphide?
yeah. Yeah, exactly. That's good. Calcium phosphide. Yep, that's what we would call it. Very good, guys. Now, sometimes you're going to run into situations where you'll go in the other direction. Okay, so they might ask you, all right, how about something like this where I give you a name and you have to go to a formula? So let me do that. We could have, for example, aluminum bromide. Now, in this case, the first thing I ask myself is what elements are involved? Obviously aluminum, so I'm going to write the symbol for aluminum. There it is, Al. Now the bromide, okay, what element is that? Oh yeah, that's bromine, right? So I'm going to put a Br next to the aluminum because I know that the formula has to contain those 2 elements. So now, what's the next thing you think I do to get the right formula out of this? Well, I got to go back and look at charges on the ions, right? So if you look at aluminum, aluminum is over in group 3A. So it's that column right next to where the transition metals end, right? Now, over in 3A, are we better off losing 3 electrons or gaining 5? I'd say losing 3. So we're going to want to lose 3 electrons for aluminum to look like neon. So that's going to give me an aluminum 3+ there. Everybody see how I got that?
Yep.
So in other words, one of the things you can do is you work across, and it depends on the periodic table you're looking at. is at this point, when you're focusing on main group elements, you want to just skip over the transition metals. Remember those pink guys we looked at? Just forget that they exist. So if you skip over those, you can see that aluminum is over in column number 3. Okay, so that's why we call it an A group or main group metal, because we're skipping over the transition metals here. Don't worry, we'll come back to them. So we got a 3+ there. All right, so bromine we've done before. We see that it's over in group 7A, so it's going to want to pick up an electron to look like krypton. So it's going to have a 1- charge. Okay, so in order to get everything to balance out, how many bromines do I need?
3.
3. So I'm going to put that downstairs as a subscript. So that gives me my 3-, which will now cancel out with my 3+. Okay, so that's how I get back to the formula. All right, so that takes care of the type 1 compounds. So the type 2 compounds work pretty much the same way, but now we're going to talk about species that have transition metal ions in them. So we're going to kind of move away from the main group, and we're going to go to the transition metal ions. Okay, so we'll call those the type 2. So these are the ones that involve transition metal ions. There we go. Transition metal ions. Those are the pink guys in the periodic table I showed you before. Now they're still metals, so they behave like metals, and we can make ionic compounds out of them, just like any other great main group metal. Now here's the problem with transition metal ions, though. They can take variable charges. The nice thing about the main group metal ions is that you can take it to the bank just by looking at where they are in the periodic table as to what the charge on the ion is going to be. So in other words, the sodium is always going to be a 1+. The calcium ion is always going to be a 2+. And aluminum ion is always going to be a 3+. There's no ambiguity about it. The problem is with transition metal ions, these can take various charges. Okay, good solid example of that is iron. So you guys probably learned back in high school, you can have 2 types of iron. You can have an iron 2, which is an iron 2+, or you can have an iron 3, which is iron with a 3+ charge. You could have either one of those, okay? So that makes things a little bit more nebulous. So for example, if I wanted to make a ionic compound involving iron and chlorine, I could have 2 options here, right? I could have FeCl2, that's the first case, or I could have FeCl3, that's the second case, right? Because in the first case, I've got a 2+ on the iron. In the second case, I got a 3+ on the iron, right? So now if chloride's always a 1-, okay, I need to have 2 of them in the first case and 3 of them in the second case to get the charges to balance out. Oh, sorry, that should be a 2- and that should be a 3-. Sorry, guys. Okay. Now, given that I could have 2 different compounds here, how do I differentiate between them? And here's how we do it. We actually have to use the very same naming scheme as we did before. So in that case, each one of these would be iron. I can't seem to write today. Iron chloride, right? This one down here would also be iron chloride. Notice I left a space there. So that's how we're going to differentiate between them. So now I have to be able to say, okay, one of those is different from the other. So here's how I do it. What I'm going to do is after the iron part, after the metal ion, I'm going to put parentheses. Okay. And in those parentheses, what I'm going to do is I'm going to put Roman numerals in there to specify the charge on the iron ion. So in the first case, it's an iron 2. In the second case, it's an iron 3. So now, by putting those parentheses in there with those Roman numerals in there, I can differentiate between those 2 iron chlorine compounds. Okay, so the first one's iron 2 chloride, second one's iron 3 chloride. So it's just one little addendum that we have to put into our naming scheme when we're dealing with transition metal ions. Okay? Everybody see that okay? So what if I did this, going the other direction? I could have nickel, let's say 4, fluoride. Okay, still ionic, right? Metal and a non-metal. But now nickel is one of those transition metal ions or atoms that we find over in the middle of the table there, the pink guys. So I can't just look at nickel and its position in the periodic table and assign it a charge. It could have any charge. Okay, but in this case, I know where I'm going because the name tells me I'm dealing with nickel 4. So I'm going to do the same thing. I'm going to put my nickel symbol in there, and I'm going to put my fluorine symbol in there. And now I'm going to assign charges. Now the fluoride is always going to be 1 minus, right? But the nickel in this case could vary, but the name tells me which charge it is. It tells me it's going to be a nickel 4 plus. Now that lets me deduce a formula because I know that I need a certain number of fluorides to make the charge balance. So how many fluoride ions do I need to balance out the charge on the nickel?
4.
4, yeah. So I'm gonna, okay, be careful there, guys. It's not addition, it's multiplication. So I got to put a 4 down there. So what am I doing? I'm taking the 1 minus charge I've got on each fluoride ion, and I'm multiplying it by the 4 of them that I have. Okay, so that's going to give me a total of 4 minus. So now the 4 plus and the 4 minus cancel. Everybody see that okay? All right, excellent. Now, there's one other type that we have to worry about here. Okay, so we're just kind of building out. We'll call these the type 3s. Type 3s are going to be ionic compounds that involve polyatomic ions. Okay, so what's a polyatomic ion? All right, chances are good that you guys learned these in high school. I'm sure in the ALEX you guys had to deal with them there as well. What a polyatomic ion is one of these things like, for example, sulfate ion. So I'll just write that down because it's a really common one. SO4 2 minus. Another good example might be nitrate, which is an NO3 1 minus. Okay, those guys look kind of familiar to you. So if you look at them, they're kind of molecular ions. So they're molecules like SO4, that's a sulfur bonded out to 4 oxygens. But the whole thing, the SO4 unit carries a 2 minus charge, which makes it an ion. Okay. Now, since it's an ion and it's made up of nonmetals, it can bind just like any other anion or negative ion to a metal ion, which carries a positive charge. All right. Now, where are these things if you want to familiarize yourself with them? All these things are over in table 2.5. You guys have probably found that already in your textbook, and that's on page 302. So your comprehensive list of polyatomic ions are over there. Okay. And by the way, that is a sulfate ion, just if I want to add a name to it. And that guy over there is a nitrate ion. Okay. So those are just 2 common ones. There's a whole bunch of them we can pull from in that table over there. All right, so what can we do? Well, we can do the normal thing. Like I say, these are negative ions, so they can bind with, for example, positive ions, which are metal ions. So I could have something like this. I could have cesium, and then I could bind it with a nitrate. Okay. So let's just make sure our formula is good. Cesium is over in group 1A, so it carries a 1 plus charge. Nitrate, by definition, has a 1 minus charge. And as you familiarize yourselves with these polyatomics, you want to remind yourself that the polyatomic has a formula, a charge, and a name, right? So NO3 1 minus is the formula. Obviously, the 1 minus is the charge that it takes, and nitrate is the name of the ion. Now, the nice thing about this is since these things are already named as ions, okay, we don't have to change the names of them. All right, so what we're going to do is the normal thing where we're going to take the element name for the metal ion, which is cesium, and then we're just going to add to it the name of the polyatomic ion. So this would be cesium nitrate. Don't have to change anything. And again, the reason for that is because the polyatomic is already named as an ion, so I don't have to change it. Okay. Now I could combine the 2 if I wanted to. I could do something like this. I could have, say, this. Ooh, that looks like a combination of a type 2 and a type 3, doesn't it? Because I have a copper over there. Copper is a transition metal. Okay, so I don't know by just looking what the charge is, but could I deduce it? Yeah, I sure could, because I know that a sulfate's always got a 2 minus charge, so I'll just put that up there. And the formula here, of course, says there's only one copper with a sulfate. So what does the charge on the copper have to be if this is the correct formula?
2.
2 plus, very good. Okay, so see how the charges cancel there. Now, if that's the actual formula, how would I name this, knowing everything that you guys know at this point? It would be copper, right? And then what do we do after the copper?
Sulfate.
And we'll put sulfate there, good. Now, is there anything else we need?
The
Need a
2.
2 in parentheses.
Yeah, I need that 2 in the parentheses, Roman numeral 2, right? Because now, since I know the copper is a transition metal ion, it could carry multiple charges. So I got to make sure I specify which charge I'm dealing with. It's in this case, and it's copper 2, and I know that from the formula. Okay, so what if I go the other direction just to practice this a little bit more? What if I had something like, I gave you the name lithium carbonate. And this is where it's helpful. If you're not familiar with your polyatomics, it's helpful to kind of have a table of them standing by so you can kind of look down the table and find these things. But knowing what I know, lithium is Li, right? So I'm just going to write down what I know. And it always carries a 1 plus charge because it's over in group 1A. Anybody know off the top of your head what the formula and charge for carbonate is, or if you have your table handy next to you? Anybody know it just off your head? It's not one you see all the time. I'll give you a second, and don't worry if you don't know it. Yeah, if you go look it up in the table, carbonate looks like this. It's a CO3 with a 2 minus charge. Okay, that's carbonate. Now, given what we know here, how many lithiums do I need per carbonate to make the charges work?
2.
2, very good. I'm going to put that downstairs here, right? So Li2CO3 2 minus, that's lithium carbonate. And one thing students often ask me is, do I have to actually put the charges up above each ion? No, you don't. That's just there for me when I'm working this out so that I know how many lithiums I need with each carbonate. So this comes up in Chem 101 when you practice it. You don't put those charges up there unless Chem 101 asks you to do that if you're dealing with an individual ion by itself or something. But when you have a compound like this, the way I would write this is Li2CO3. So again, I put the charges up because I like to see them, but you know, for a proper Chem 101 answer, you would actually write this. Okay. All right, so those are the 3 types of ionic compounds that we can deal with. Any questions about that before we practice a little? All right, let's pop out back to Chem 101 here for about the last 15 minutes of class. I have 2 exercises there for us to work with. We'll just kind of open them up and see where we're at.
So basically, hello?
Yeah, go ahead. Keep going. I'm just messing with Chem 101 here to get us where we need to be.
Oh,
All right. We're running
okay.
that first one.
Hello?
Yeah, go ahead.
Two problems. Are we always going to be given that charge like
When you say the charge
the
thing,
S already?
yeah, your sound's
Like
kind of
for
breaking
copper,
up.
copper sulfide, right?
Like for copper.
Can you hear me now?
So
Yeah, you already.
yeah, your sound is coming and going. Actually, if you want to, pop it up over pop your question up over in the chat, and I'll go over there and look at it, and then I can address it there, because yeah, I can't hear you. Your sound's coming and going. So while everybody's working on this, you can pop that over to the chat and I'll go look at it. Where'd my Zoom go? Here it is. And I can toggle back to that. These ones are all your type 1s here.
Oh, Professor, can I have some help on the last one?
Sure thing. The cesium phosphide one.
Yeah.
Yeah. So you want the chemical formula, right? So,
yeah, I have CS3 and PO4.
All right. So you got your cesium phosphide. So let me actually scratch this out. Cesium carries what charge? Just working it from the top, right? Cesium's what?
Cesium is, let me find it on the table.
Yeah, it's over. I'll give you a hint. It's over on the far left.
Okay, as it's in the first column, so 1.
Got it. So it's going to carry a 1+ charge. So go ahead and put your CS with a 1+ over it. Now, what element does phosphide relate to? Which element are we talking about there?
Phosphorus.
Phosphorus. So where's phosphorus
In
relative?
the 15th.
Okay, so what does it have to do to look like it's going to get back to a noble gas? Is it easier for it to gain or lose in this case?
Gain.
Gain. How many? Just count across.
Count across left to right.
Count across to your right to get to your nearest noble gas.
3.
It's good. So that's going to put a charge of what on your phosphorus?
3.
3-. Okay, put that over it.
Why is it? It has the gain 3, right?
Yeah, sure does. And that's why, see, every time you put a new electron in there, you're gaining a unit of negative charge, aren't you? So that's why we're going to put a 3- on there, because we're adding 3 electrons into a neutral atom.
Okay.
Make sense?
Yeah, so it would be CS1 and then PO3.
Be
Right?
careful.
Or
How
PO
many
negative 3.
cesiums do you need to balance the charge on the phosphorus, on the phosphide?
You need 3.
Yeah, so the 3 goes under the cesium, doesn't it?
Okay. And
Yep,
then
you got it.
PO minus 3.
So you're going to end up having a CS3P. I think that's what the answer is. Yep, sure is.
All right, and the can you also help me with the first one, please?
Yeah, that's the aluminum nitride.
Yeah.
Okay, and that's it.
Oh,
So-
okay, there it goes. Okay, I got it. I put the wrong thing in. I'm sorry about that.
No problem. I'm going to open up the second one now here, because that's going to give you some dealing with transition metals and polyatomics. So I'm sure a lot of folks already finished with the first one. So we'll go ahead and open up the second one here. And you see how far you get with this.
Professor, does the time matter if they expire?
Yeah, it doesn't matter in terms of a score or anything. If it expires and you're not
yeah.
finished, don't worry about it. You're not docked anything. This is just practice, right? So in other words, take your time. Don't feel like you have to finish everything in front of you. Some folks will get finished, others won't, and that's perfectly okay.
When do we use the Roman numerals?
When you're dealing with a transition metal ion. So remember, those are the ones that are those pink ones in the periodic table I showed you that are sort of in the middle of the periodic table.
Okay.
Yeah, and those are the ones that can carry the variable charges. So that's when we use your Roman numerals. We never use it for a main group element because we always know what the charges of those are.
So for
Either position
the
on the table.
oh sorry for the
Go ahead.
CO and like CL2 for the first one, it would be cobalt. How do you tell like what parenthesis to use?
Or which number to use in the parenthesis?
Yeah, for like cobalt, for
Chloride.
Cobalt
Yeah,
chloride.
so you'll put cobalt parentheses chloride. So then what goes in there? So how do you deduce that? Well, you have to deduce it from the other thing, right? So if you've got a chloride, right?
Yeah.
Okay, what's the charge always on a chloride? Always.
Oh, like 2.
Careful.
-2.
Getting closer. It's negative.
-1.
Yes. And how many of them do you have in the formula?
2.
2. So what's the total charge above the chloride?
-2.
-2. And how many cobalts do you have per chloride in the formula?
You would have to have 2.
So you have to have 2 units of positive charge, but they have to be spread across a single cobalt, right? So what goes in the parentheses now?
2.
Yeah, you got it.
All right, thank you.
You got it. Just takes a little practice. Once you've done 4 or 5 of them, it's easy. That's the thing about chemistry in general. It's just kind of following protocol. We're big on rules. Yeah, you guys are banging away at this.
So Professor, on the chromium, its charge is determined by is its charge determined by where it is, like on the table, or is
Actually,
it?
in the case of the chromium, it isn't, because if you find chromium in your table, it's in that middle section, right?
Yeah.
Yes, that tells you it's a transition metal. So what we
Mhm.
know about transition metals is they can carry variable charges. So in that case, you can't just look at it and say, well, chromium's going to have a 2+ charge or a 3+ charge. It could actually could have a 6+ charge. So how are
Okay.
you going to deduce it? Well, you have to work from the point of view of the nitride, the nitrogen, because
Gotcha.
that one's main group. So you always know what it's going to be.
Gotcha. Okay. So would so the nitride would be let's see, would the nitride just be a 2? I
So find
believe.
it there, and it looks
Yep.
like you're better off adding electrons than losing them, because it's kind of over on the right hand side.
Yeah.
So so let me ask you this: how many electrons do you have to add to nitrogen to get it to look like neon? You're moving across the table left to right.
So it's a +3.
You got the 3 right. Yeah, you're going to need 3 electrons. But remember, electrons carry a negative charge. So if you're adding 3 of them, you're actually making it a 3- because you're bringing 3 units of negative charge in.
Oh,
So your
okay.
nitride ion, you're right about the 3, but it's a 3- instead of a 3+. So if you put the 3- above it, what's the charge on the chromium have to be?
The charge of the chromium then would have to be a +3.
You got it.
Okay.
You got it. So see how you kind of work backwards sometimes to get at it? There's always going to be something you know. So you can always work from the standpoint of the thing you know to get back to the thing you don't.
Okay. Thank you.
Mm-hmm. No problem. All right, so as we close out today, keep in mind that your next video is going to actually be on naming the other kind of compound which we have, which involve nonmetals. So those are covalent compounds. So we're going to focus in the next video on how to name those, and then we'll practice with that a little bit more in class, and then move on to the next topic. So be ready for another 5 for 5 quiz on Wednesday, guys. And you pretty much know what it's going to be on, right?
The 5 for 5 quiz is on the stuff we just learned, right?
Yeah, and also
good.
I can put something on there about the video you're going to watch for Wednesday. So make sure you do that. Yeah, so it's today's material plus whatever's on the video for next time. All right, any other questions before I head out, guys? And this is open for another minute or two, so feel free to continue messing with it if you like. All right, and Tio asked, are we going to be given the charge on the polyatomic ions? Depends on whether I let you use the table or not. And initially, I think I will let you use the table until we get used to them. So they'll always be there for you, buddy.
Thank you.
You're welcome.